Look at a modern living room. We are surrounded by devices built explicitly to connect us to the rest of the world, yet the immediate result is often a room full of people sitting in isolated, device-locked boxes. Standard critiques often blame user behavior, the so-called digital bubble. In reality, this isolation stems from software architecture that fails to account for human social mechanics. Successful interaction design relies on a specific premise. Human conversation runs on a set of deep biological rules. For a digital interface to facilitate connection, it has to accurately map those implicit physical rules onto its software. When we talk in person, the process feels seamless. But when we communicate through software that fails to map those physical rules, the brain has to work overtime, generating a massive cognitive load. To understand why certain apps feel natural and others exhaust us, we need to reverse engineer human conversation down to its base code and evaluate how modern interfaces try to emulate it. Integrating sociology into the engineering process resolves the friction between human users and communication software. In 1978, Harvey Sachs published Conversational Analysis, acting as the source code for human turn-taking. Interaction operates like a state machine with 3 rules: explicitly selecting the next speaker, another person self-selecting to speak, or the current speaker continuing. But the data stream of conversation requires more than just turn-taking. It relies on a suite of secondary, invisible mechanisms to keep the interaction from breaking down. One of these is back-channeling. These are the non-intrusive verbal and physical signals, like nodding or muttering "uh-huh," that confirm someone is actively listening without triggering a formal turn-take. Another mechanism relies on implicit physical cues. A subtle shift in eye gaze, leaning forward, or fidgeting with a coat allows participants to anticipate exactly when a conversational turn is about to end. These rules run effortlessly on automatic biological hardware. Stripping them away in a digital environment guarantees a system crash, unless designers explicitly engineer replacements. You can see this system failure clearly when we try to force map those physical rules onto a flat 2-dimensional video grid. Researcher Jeremy Bailenson defined Zoom fatigue as an intense cognitive load triggered by interface structural failures. Camera placement in a grid creates mismatched gaze trajectories, making mutual eye contact impossible. Furthermore, staring at your own video forces continuous self-evaluation. The 2D grid inherently flattens out spatial depth. That strips away our peripheral awareness, making it impossible to track the subtle implicit cues we rely on, like watching someone's chest rise as they take a breath to speak. To fix the resulting conversational pileups, software designers implemented a heavy-handed workaround. They took fluid, implicit physical cues and turned them into rigid, explicit digital rules. The widespread adoption of the raise hand button during the COVID-19 pandemic was exactly this, a brute force software patch designed to fix broken turn-taking. Likewise, clicking a heart or a party hat icon that floats on screen for exactly 10 seconds acts as a synthesized, highly structured form of back-channeling. Video conferencing drains us because the user interface forces our conscious, analytical brain to manually execute turn-taking tasks that evolution designed to run smoothly in the background. Interaction design draws a sharp line between 2 concepts. Telepresence, which is simply establishing an audio-visual connection between remote locations, and social presence, which is synthesizing the actual feeling of occupying a space with a real entity. High visual resolution isn't always required to achieve this. Text-based conversational user interfaces can synthesize a strong sense of social presence with 0 visual fidelity. This is an interface for an AI chatbot. Its ability to feel present relies entirely on flawlessly emulating that initial sociological model. By trading short, alternating messages and confirming inputs, it executes programmatic, perfectly symmetrical turn-taking and back-channeling. While text interfaces succeed by simplifying the rules, hardware designers are tackling the failures of the 2D video grid by increasing physical fidelity. This is a high-fidelity telepresence display, designed to restore one-to-one scale and spatial proximity. Notice the embedded camera placed precisely at the top of the box. This specific architecture corrects the eye contact trajectory failures we see on standard laptops. By capturing and projecting the full body in a localized frame, This hardware actively restores the viewer's ability to track implicit cues, such as natural gaze shifts and changes in body posture. Achieving true digital presence depends on accurately reconstructing the biological sightlines necessary for human coordination. Resolution alone cannot bridge the gap if architecture ignores how humans actually look at one another. These principles also apply when people are occupying the same space. We shift here from remote communication to co-presence, the practice of augmenting groups working simultaneously in shared physical or digital environments. In 1992, researchers Dorish and Bly mapped out how humans manage these spaces using awareness mechanisms. In high-stakes environments like operating theaters or air traffic control, teams navigate around one another smoothly without explicitly speaking. This reliance is heavily based on our peripheral awareness. Team members keep an ambient track of others' actions in the corner of their vision, adjusting their own movements to prevent workflow collisions. This is a shared Miro board. Software like this attempts to recreate peripheral awareness in a virtual space. The live, floating cursors moving across the layout act as digital stand-ins for human motion, letting you know exactly where your team is working without asking them. Interaction design can also moderate how we behave when physically sitting next to each other. Take the reflect table experiment. This shareable interface utilized microphones placed in front of each user to track who was dominating the conversation, lighting LEDs in front of the group's most active speakers. The behavioral outcome was immediate. By taking implicit conversational imbalances and making them explicitly visible on the table, it forced the heaviest talkers to self-regulate, resulting in more equitable participation. Effective co-presence design doesn't step in and replace human interaction. It creates visual feedback loops that allow human groups to self-correct and coordinate their own behavior. Every technological leap in interaction design attempts to bridge the gap between rigid digital constraints and fluid social mechanics. Whether we are typing in text chat, navigating a video grid, organizing a Miro board, or stepping into a holographic display, each interface plots differently in how it supports our awareness and presence. To evaluate where any future social interface lands on this matrix, game designer Matt Ricchetti proposed 3 specific heuristics. First, does the system force synchronous interaction or asynchronous turns? Second, is relationship formation symmetrical, requiring input from both sides, or asymmetrical? And third, does the UI facilitate strong, deep relationship ties or weak, transitory engagements? By identifying these variables early, designers align software with the social expectations of the human brain. Ignoring this rubric is what creates the isolating friction common in modern interfaces. The ultimate goal of interaction design is the seamless, invisible integration of these biological coordination mechanisms. True success allows humans to persist in being social without ever feeling the cognitive friction